what's kind of interesting is that the identity is this. So when you convert the WKB into this thing with a Z in it, what's kind of interesting is that when you figure out how to express the limits in Z, you naturally want to put 1 plus square root of E over D on top and vice versa. You kind of just want to do that. That's actually incorrect. The minus one's on top. And if you get a switch, you're going to pick up a minus sign. And that'll be wrong. So that's what actually Abdul figured that out. He felt like double checking what I had done. And he found, he's like, hey, you got a minus sign there. And it took me a while to figure out what I had done. So the neat thing is, when you figure this out, you end up like with a minus the square root of a square. And so when you have the square root of a square, it's always plus or minus. But you have minus that, you got to go minus plus. And so that ends up being on top. I also wanted to point out that Z is e to the minus, what the hell is it? A x minus x naught. Okay. Let me point out something too. So remember, you got to get these limits right. Okay. Now, in the WKB integral, this is a high x and that's a low x, like normal, and that makes sense, right? But here you see that this is a low z and that's a high z. So it's opposite. And again, I'm just emphasizing this because you have to get this right. Doesn't make sense. Okay. If x is a big number, z is a big number, small number?
Small.
Right, because I got minus a big number. If x, let's make it a small number, like a negative number. Let's make it negative infinity. Z is positive infinity. So small number, big number. All right, so it makes sense. Okay, this ends up being square root of 2m over h bar. You may notice a h bar. You can, the constants just come out. I didn't know if that was obvious. Square root of d minus e. Now, for reasons I explained in class, when you're doing a particle in a box, that integral, the entire WKB integral, the boundary condition just says you have to be a multiple of n pi, but for weird reasons that are really hard, that are just bonkers, on a vibrational type system, you end up with n plus a half. And is that right? I'm doing that from memory. I just gave a big speech about how this has to be perfect.
Like the phase shift or whatever.
Yeah, it's a phase shift. All right, you got to do it.
I don't think I can do it.
Yeah,
I
you
can do
can.
any of the other questions, not this one. No.
Yeah, it's got to be yours.
I don't.
Yes.
I don't think I can do even the limits.
You just wait. What are you talking about? You don't do any integrals. You just go from here to here. This is what you said you had a problem with.
I think so.
Right.
No, I'm totally confused. I can't do it.
Wait. Okay, so you set up the WKB.
Yes.
You do this substitution.
Yes.
You get this. Right? And you told me you got here. You guessed you did or you didn't?
I guess.
You did not. Okay, so you're stuck at the beginning. Okay, that's because this is really, when you're here, you're at the end.
Oh no. I guess. No.
Okay, you're stuck at the beginning. All right, well, let's go through that. Okay, WKB. I'm not going to remember it off the top of my head. Okay, it's clear that 2m e minus v d over, is there an H bar in there?
Should be, yeah, should be
There.
over equal.
Should be an 8 divided by H bar?
Yeah. You have it in the top part, like in your identity, yeah.
Yeah, I have to admit that bothers me a bit. There's that P and a K, and, yeah, and this was K, right? And then you had, the low turning point and the high turning point, right? And so, now remember, the reason that this picks up a half here is that the particle in the box, the turning points were the boundaries of the box, and the wave function came to an end. But in a vibrational deal, even a Morse potential, the wave function can go past, the wave function is defined everywhere. It doesn't hit zero, and it doesn't hit zero anywhere, ever, which is weird, but, so that's why you pick up this 1/2 here deal. Okay. Now, again, the reason I asked this question is, when I took it again, we were just asked to solve it. But I looked at this and I thought, well, what if I forced you to learn a little bit more mathematics? Okay, so anyway, before we set it up, and as I mentioned in class, you got to get the turning points. Okay, so that's when E is going to be equal to the potential energy. E1 minus E. Okay, so E over D. No.
No, yeah, you
Just that, right? No, wait a minute.
No, the square is the outside of the premise. Yeah. Like that whole thing is squared. 1 minus E minus A exponential. The whole thing's squared.
Yeah, this sucks.
Yeah, I know.
Okay, 1 minus 2. It's actually not that bad because it's not that bad because it's not complex. Well, if it was complex, it would just take a little bit longer. Okay.
Why would
You know what? That's stupid. Do this. Right?
Yeah.
Yeah, that's a hell of a lot easier. All right. Okay, now we take the natural log. And this is the turning point at this point. Okay. I had to be more careful. Plus, minus, plus, minus. Plus, minus. Plus, minus, right? Okay, so there's the turning point. Plus for the high one, minus for the low one. Okay, so again, why are you doing that?
I just couldn't see.
Oh, okay. Excuse me. Okay, so, blah, blah, blah. So now here's what I did when I was in grad school. Once I had gotten this far, I plugged the high turning point and the low turning point in here. I typed this into MathCAD and hit go, and I got the answer. And then I had to do some, which is this, and then I had to do some more algebra to get E, to solve for E. which will have D and H bar and A in it and M in it. Okay, but what I want you to do is show off some, remember, we value concepts, but we also value mathematical prowess. So I wanted you to turn this into a thing of Z. Before I do that, I actually need to make sure that I know what the right turning points are. There's two of them, and one's high and one's low. I got to get that straight. Okay, so let's see here. The plus one would be the least negative, and that would be the high. Yeah, that would be the highest number. And E is less than D, I think. Is E less than D? What did I?
It should be, yeah.
D is less than
Yeah.
D. D is the well depth, right? Yeah. So, wasn't that? Wait, can you take natural log of a negative number?
No, it's-
Did
I didn't know why you did the ln, so, I mean, I just got the turning points by substituting Z in, and then when I did the substitution, I just plugged them into the higher number, or the upper and lower bounds.
Yeah, I see. 1 second.
Yeah, yeah.
I see what I did wrong. Okay. Okay, dumb. Okay, I'm okay here. And then I subtracted. Okay, so here's where I screwed up. I subtracted 1, but there's a minus sign here. Right? You see, I forgot that. I subtracted 1 from both sides, but I saw the minus sign. Okay, so here's how it goes. Minus plus. So this is what I was talking about. There we go. And so you really got to do that. So again, when you take the square root of something, right. So because if I work backward, I end up squaring this. So anyway, minus plus. Okay. Plus. Okay. Right. So this is going to be probably less than. So it can be a big number, which is plus. But then that minus out here makes it the small one. So, let me just double check my notes. I feel like so that makes the plus the lower limit. Yeah, that's right. So the lower limit is going to be minus 1 over A natural log plus, so I don't have to put anything. I got plus x naught. I'm just messing up my algebra. Let me double check again. Yeah, okay. Now the higher limit is then minus 1 over A. Minus 3. Make it a little bit easier to look at. 1 plus 1 minus. Okay, now the reason is, again, this is a small number. Let's say, okay, so this would be like 0.1. Let's call this like 0.1. What's natural log of 0.1?
What's that?
Oh shit, that's minus.
It's minus 2.3.
What makes this? And then what would be natural log of 1 is 0, right?
Yeah.
Yeah, I don't know, so if I say that the plus is my higher limit, but I just follow a natural progression, I ultimately get this, right? Because I end up switching plus and minus because of that minus right there. Okay, well, let's just go with this. All right, so I have the turning point. So the reason I'm harping on this is that you have to get this right, and this is right, by the way. And when I first wrote the problem set, when you looked at it, I actually had it wrong, sorry, but I didn't have that there either. Okay, so anyway, so you had to figure this out. Now the problem was, again, I switched it to a math problem so that you got better at math. And I've already defined z, right? We're going to do that. Didn't I already define z? No, whatever. E to the, what did I do? I don't want,
It's anything but.
yeah, I don't want to start writing things down. Okay, all right, so when you do that, let's see what happens. Being confident in terms of a substitution in an integral is something, if you can't do that, I don't think you should be getting a PhD in all honesty. Okay, we're going to worry about the turning points in a little bit. 2m over h bar, let's just make that easy. E minus d, 1 minus z squared, right? Yeah, okay, and I did do it right. Okay, now here's the problem, right? Let's do the Jacobian, right? So you remember you have to do the Jacobian, right? You just can't write down dz. The way you do that is you need to convert dx to dz. And you would do that by this. Here's your Jacobian. Dx dz. Okay, and we'll worry about the turning points in a little bit. Okay, so let's do that part. Dx dz. That means I have to get x equals and then a bunch of junk with z in it. Okay. Where'd my z go? Okay, well here, I'll just start here. ln z minus a x minus x naught. Okay. Minus 1 over a ln z plus x naught equal to x. Is that right? Okay. Therefore, the derivative of x with respect to z. Oh, shit. No, that's not that hard. Minus 1 over a. Derivative of z is 1 of natural log is.
It's 1 over.
Oh yeah, right. Yeah, it's right freaking there. Okay. There we go. Oh. All right. And the next bit, limits. Okay. Okay, so I have, how the hell do I do this? So I've got those two x's, and I've got to get them now in terms of z. So remember that the limits are not different. You can't change them. You just got to find the same damn thing with the letter z in it. So, how would you do that? I think I'm just going to solve for z. Let's do okay. All right, so it's always easy to scratch out minus x naught on both sides. Okay, the arguments have to be the same. Well, this ended up being really easy. And then the same for the... All right, that's it. Now you've got the identity. All right, so last bit I want to point out is the way to not screw this up. So when I was doing this, I chose one plus square root of E over D on top and one minus square root of E over D on bottom because that one was bigger than that one. But again, Z and X are anti-correlated. X is big, Z is low. So it makes sense that the lower one's the upper limit and the higher one's the bottom limit. That makes sense for that reason. So it makes sense for multiple reasons. For one, Z is high when Z is low when X is high. Z is high when X is low. So that makes sense. But the way you really do this, which is a biz knocker, is you have to follow it from here. You've got to keep track. At this point, you've decided, you've identified why you're going to find two X's. Whenever you've got, this was squared, whenever you've got something squared, you're going to have two answers, right? A plus and a minus. Now, it's fine at this point to say, okay, the upper limit's plus. And you just got to follow the damn thing through. It's just that you're going to end up multiplying it by a minus sign, and that switches the roles. Which, I need to delete it there anyway. I was speaking out loud and then, yeah, anyway, that bothers me. Yeah, so there you go. And then you're, and then that, yeah, now we're here. And here, then you just solve for E. Yeah? Does that answer your question?
Yeah.
Okay, so I didn't know what your question was, so there you go.
I think I was stuck at the very beginning. I tried doing many things, but nothing was.
Well, yeah, so WKB, so this is the K vector. K vector, so you're integrating the K vector from one turning point to the next. And in the particle in the box, that was 0 to L. In this, it's what we just figured out. The K vector is really, P is H bar K. So P over H is K. P is going to be, P squared over 2M is equal to the energy available, and that would be E minus V. Right? Because kinetic energy is P squared over 2M. The total energy minus the potential is the kinetic. So, yeah, square root of 2M E minus V naught, V of X, square root. Okay, so that's P. To get to K, you just divide that by H bar. Yeah, so anyway, oh, there's another parenthesis, I have to add that, or it's not right. And I'm going to freak out.